Hi, hello students. Welcome to BYJU'S Exam Prep. This is Anil Prasad Sir. In today's session, we are going to have a complete recap of computer organization and architecture in terms of CPU design. We are going to solve many of the questions in order to have a complete grip on CPU design in the topic computer organization and architecture for all the aspirants of BARC HAL 2022. Just to remind you, we do have a strategy to conquer session for GATE 2023, which is going to be streaming live on 30th March, which is going to be taken by our well famous Abhinav Negi sir. Don't miss this session because you're going to have a complete idea how to prepare for and what are the strategies that have to be followed for the GATE 2023. Yeah, let us start with CPU design. You know that CPU design is an important part in the computer architecture and organization. Hi, good morning, good evening, everybody. Yeah. So let us start with the CPU design. The questions from the CPU design. Yeah. So in order to brush you up, first of all, in order to design the computer system, we will start with the CPU design. Within the CPU, we are going to design three entities. That is, the first one is the register set, second one is ALU, and the third one is the control unit itself. And when it comes to the CPU register set is actually used for storing the concurrent instruction with the associated data, and the ALU is used for performing the operation during the execution course of the instruction. And finally, the control unit. The control unit is used to synchronize all the activities and all the entities of the physical entities of the computer system. And now let us start with the CPU design. The first question that we're going to solve in the CPU design is as follows. A processor has 40 distinct instructions and 24 general purpose registers. A 32-bit instruction word has an opcode, 2 register operands, and an immediate operand. What is the number of bits available for the immediate operand field? Can I have, hi Durga Prasad, can I have the answer for this? Can we have a quick look at the answer for this? Here, what are the details that are provided? The details that are provided is a processor has 40 distinct opcodes and the processor has 24 general purpose registers and the instruction size is 32-bit. And in every instruction, we do have an opcode and 2 register operands and 1 immediate operand. So, in this case, the question is the number of bits available for the immediate operands. We are asked for what is the total number of bits that are available for the immediate operand field. Let us have a look at. For this, let me draw the block diagram of the instruction. Let us see the total number of bits of the instruction as given in the question is 32, right? We do have a 32-bit instruction. Now, of course, you people clearly solved this. Of course, it is A. But I will give you a shortcut for solving all these things. These questions, we can easily solve. We don't need to solve any. We don't need to apply any formulas, or we don't need to turn the world upside down. Simply, we can solve. I'll give you. First of all, just draw the block diagram of an instruction and divide the fields. First of all, identify the fields. The first one is opcode, of course, and the next one is register 1. Sorry, I will write the register 1 here. And I will write the register 2 here. The final one is, which is called immediate operand. I will say IMNOPR, immediate operand. So here, what are the things provided? Total number of registers are 24. Number of registers are equal to 24, which means that we do require 5 bits in order to represent one register, right? Because if we represent the register with 4, we will be able to represent a maximum of 2 power 4 registers. That is 16 registers will be able to represent. And if we use 5 bits for register field, we will be able to represent a maximum of 2 power 5 registers. So the number of registers is in between 16 and 32. We should take the maximum number of bits that are needed to represent the total 24 registers. That is 5. Although some of the combinations are not used, but we'll go for 5 bits here. I hope you got me. Okay, so register 1 is 5 bits, register 2 is also 5 bits. So register 1, register 2 will collectively take 10 bits each, and the number of the machine language instructions are 40. If I do have opcodes, I will say opcodes are equal to 40. Okay, this 40 is in between 32 and 64. If the number of instructions are 32, I will use 5 bits. If the number of instructions are 64, I will use 6 bits. But it is in between 32 and 64. So although some combination will get wasted, I will still go for 6 because we should be able to provide as many bits as required in order to represent all the possible opcodes. So here I do require 6 bits for opcode, next 10 bits for register 1, register 2, and the remaining 16 bits for immediate operand. I hope you got my point. Yeah, very good. You solved it instantly the moment I started itself. So let us go ahead with the next question. Did you understand this question? Can I go to the next question? I guess so. Hi Anu, hi Durga Prasad, hi Anjali, hi Satyam, hi Arnab, hi Bhumi. Next, here this is a good question. In fact, we have to think. We need to do some practice in order to solve this question. Let us solve this question. That is, consider a processor with 64 registers and an instruction set of size 12. Each instruction has 5 distinct fields, namely opcode, 2 source register identifiers, 1 destination register identifier, and a 12-bit immediate value. Each instruction must be stored in memory in a byte aligned fashion. If a program has 100 instructions, the amount of the memory in bytes consumed by the program text is. Let us have a look at it. Now, understand a few terms. Solving this question is, just a matter of seconds, but we should be able to identify the technical terms as are given in each question. So sometimes terms that are referred to be in some question in some paper might be different in some other paper. That is, in GATE, they might refer the opcodes as instruction set. In some other exam or in some other paper, the designer of a question would stick to some more possibilities. That is, if I call the machine language instructions are opcodes, in some other computer architect might prefer another suitable field. That is, he could use machine language instruction or instruction size or opcodes. He can do anything. But if you talk about instruction set, this instruction set is actually talking about machine language instructions. Let us understand this precisely. Either you call it as a machine language instructions or you call it as the opcodes. Okay, and there could be anything, but you need to be able to identify what exactly he is referring to. It could be machine language instructions or opcodes or instruction set. All are referring to the total number of machine language instructions that are being supported by one processor. So here, the opcodes that are being supported by this processor is just 12. Okay. The next thing is, each instruction has 5 distinct fields. Without having any ambiguity, we will directly go to draw the block diagram of an instruction. 500 is correct, but I'll give you another dimension in solving this question. Let us understand. What is the total number of fields? There are 5 fields. The first one is opcode. I will write it here. Second one is what? Register 1. Third one is register 2. And the fourth one is register 3. And the fifth one is immediate operand. I will say IMM OPR. So these are the 5 fields. First of all, go for the opcode. How many opcodes we do have it here? We do have 12. 12 meaning again it is in between 8 and 24. Okay, 8 and 32. If it is 8 and 16, mind you, bigger pattern. If it is 8, I can represent these opcodes with the 3 bits. If it is 16, I can represent these opcodes with the 4 digits. But anyhow, as 12 is in between 8 and 16, I need to use these 4 bits, although some combinations are left over. So, number of digits that are needed to represent the opcode is equal to 4. And as you can see in the question, I do have 3 registers, 2 are source, 1 is destination. So total number of registers are how many? 64 registers. If the number of registers are equal to 64, I do require 6 bits to represent the registers. That is, I don't know what is happening. Yeah, 6 bits here and 6 bits here and 6 bits here. So 6 plus 6 plus 6, 18. 18 plus 4 is equal to 22. Okay, so total 22 bits are already used, already consumed by opcode R1, R2, R3. And immediate operand field, you don't need to calculate, already it's been given as 12. If I'm not wrong, it's immediate operand field, 12-bit immediate operand. So this is equal to 12. The total number of bits are equal to 34, right? I do have a total of 34 bits. Okay, listen to me carefully here at this point. What is happening? Just a minute. There is some technical glitch. Without my knowledge, it's been moving. The slide is moving. So let me avoid this. Yeah, stay focused. I do have 34 bits. In order to, have these 34 bits, how many bytes are actually required? Let me tell you one important thing behind this. What is the smallest measurement of storage in the computer system? May I ask you, what is the smallest measurement of storage? It's a bit or byte. You don't need to answer. Let me tell you straight away that the smallest measurement of storage in any computer system is a byte. It's not a bit. Bit must be a part of a byte. Let us understand, in order to store something, I do require a flip-flop. A flip-flop can store either 0 or 1, but you can never arrange a flip-flop. You can never organize a flip-flop separately somewhere in the computer system. In order to organize any of the data, first of all, we need to accumulate 8 flip-flops together. That is, we need to obtain at least 8 bits together, because the smallest measurement of the storage within any computer system is a byte. Okay, so in order to have 34 bits, I do require 4 bytes plus 2 bits. Did I make it myself clear? So in order to have these 34 bits accommodate in the computer system, I require 4 bytes anyhow. Is it visible? Or is it abstracting my this thing? Fine. Is it visible? I will write it here otherwise. 4 bytes. Stay focused. Let me tell you. 4 bytes are equal to 32 bits. Plus, I do require 2 additional digits in this case. Okay. For representing one complete instruction, I do require 34 bits. Right? But for 32 bits, already 4 bytes are consumed. Okay, for these 2 additional digits, what to do? You don't have to do anything. You need to obtain the complete byte. So, in order to represent 34 bits, I require 5 bytes. For one instruction, I require 5 bytes. Right? The instruction register size within the processor must be equal to 5 bytes. Okay, so when you write a program in the main memory, here in the question it is given that a programmer wrote his program with 100 instructions. As each instruction consumes 5 bytes, 100 instruction consumes 500 bytes. Got my point? Did you understand this or not? I hope you got my point. Did you understand? Can I go to the next question? Very good, very good. So this is the fundamental. This is the thumb rule behind any of the storage. Let us start designing the main memory. Let us start designing the CPU registers. Let us start designing something else. If it is a storage, if the term is associated to storage, understand something, forget about everything. The smallest measurement that you need to consider is the 8 bits. You can't organize any independent bit less than 8 bits separately. If you have to store at least 1 bit, if you have to store at least 2 bits, no matter what, you have to obtain 8 bits together, which is going to make up 1 byte. So here in our case, 500 is the correct option and the correct answer. Next. Okay. Yeah, what is this question? Let us read it. Consider a processor with the byte addressable memory. Sir, what is byte addressable memory? What is byte addressable memory? Let me tell you. The convention of memory addressing. Let us say Bhumi is designing. Let us say Anu is designing. Let us say Anjali is designing their own memories. Okay, they started designing main memory. They can have the own convention of addressing each of the location in the main memory, because every location of the main memory require a label. Our home requires an address. Our home requires a label to be addressed, right? So our postal department uses a convention, street or the area or pin code or whatever. Main memory also, in order to address each and every location, follows some conventions. That is word addressing and byte addressing. Sir, what is word addressing? Let me give you a clear idea. I will take the help of the CPU architecture. Okay. Most of the times when you go to the market and purchase CPU, they will talk, the measurement of the CPU, rather, they will give you the CPU details in terms of the size. CPU size is 32 bits. Okay, our architecture size is 32 bits. Whatever you call. If the CPU has 32 bits, that meaning one location in the main memory is equal to 32 bits. For that CPU, let us say I have i3, you have i5, somebody has i7. They will talk in terms of the size of the CPU. They will talk in terms of size of the architecture. If the size of the architecture is 32 bits, it can also be called as a CPU size. That means that one register size is equal to 32 bits. If one register size is equal to 32 bits, one main memory location size should also be equal to 32 bits. Okay. The architecture size will talk about how the main memory is organized, how the register size is designed. So here, if you talk about a CPU size or architecture size, that will actually talk about one register size in the CPU or one main memory location size. Okay. Now, let us say already as we are designing the main memory, we need to find out one convention for addressing, one word addressing or one byte addressing. If the main memory is byte addressed, each and every byte of the main memory will be addressed regardless of the size of the word. Okay, for that I will use some illustrative slide. Okay, let me draw. This is the main memory and this is one word. Okay, what is the size of the word? According to the architecture, it is saying 32 bits. One word size is equal to 32 bits. 32 bits meaning 4 bytes, right? Now let us talk about word addressing. If it is word addressing, it doesn't consider what is the number of bytes that is going to make up one word. It will give one unique address per word. So first location will get one address. Second location will get second address. Did you get it? This is all about word addressing. What is byte addressing? When it comes to the byte addressing, each and every byte in the word will be given a unique address. That means that every word in our case will get 4 addresses. The starting address will be 0. Next address will be 4 because this word has got 4 addresses. I hope I made it myself very clear. Did I? Yes or no? Did you get this? Very good. Anjali, Bhumi, Anu, did you understand this? What is the difference between byte addressing and word addressing? Shall we go ahead and solving the question? Yeah, here he's talking about byte addressable memory. Assume that all the registers including program counter and program status word are of size 2 bytes. A stack in the main memory is implemented from the main memory location 010016 and it grows upward. Okay, and the current value of the stack pointer is 016E16. The call instruction is of 2 words. The first word is the opcode and the second word is starting address of the subroutine. One word is equal to 2 bytes. The call instruction is implemented as follows. Store the current value of the program counter in the stack. Store the value of the PSW register in the stack. Load the starting address of the subroutine in the stack. What is the question asked here? The question is the content of the PC just before the fetch of the call instruction is 5FA016. After execution of the call instruction, what is the value of the stack pointer? This is very simple question. You don't need to, turn the world upside down to solve this question. It is one of the very fundamental question, but only the thing is, it is looking lengthy, right? It is just looking lengthy. You don't need to, feel confused about this question. With this, with a small main memory block diagram, we will be able to understand this very easily. Let me draw the main memory block diagram once again and follow the steps that I'm following for solving this question, so that you will be able to understand it. Okay. Now he's talking about a stack, memory stack, right? We do have two kinds of stacks. One is CPU stack, which is implemented within the CPU, which is internal to the CPU. One more is a memory stack, which is internal to main memory. So he is talking about one main memory stack. The main memory stack origin is 0100. The stack is located at 0100. Okay, and it is growing upward. What is upward? Upward stack meaning during every addition, that is, when you push an element into the stack, stack pointer will get updated. Write it down somewhere. There are two different kinds of stacks: upward stack, downward stack. Sir, what is upward stack? Upward stack meaning when you add an element into the stack, stack pointer will get incremented. When you pop an element out of the stack, stack pointer will get decremented. Sir, what is downward stack? Downward stack meaning when you push an element into the stack, stack pointer will get decremented. When you pop an element out of the stack, stack pointer will get incremented. This is the design logic. Most of the people nowadays, they are preferring downward stack but not upward stack. I will, in some sessions, I'll explain more about this stack, but this is an upward stack. This is our conventional stack, what we have been using right from our first year. This is upward stack. We know that. What is the stack pointer? Thumb rule, we know that every time when an element is added into the stack, stack pointer will get incremented. Okay, so we don't have any ambiguity here in this. Stack pointer, current top of the stack is 016E. 016E. Yeah, BARC and GATE are having very similar question pattern, and of course the syllabus is expected to be the same, and the complexity of the question is also expected to be the same. So if you can follow the GATE syllabus, you will be able to solve the BARC very easily, and the complexity is more or less the GATE question. 016E. What is 016E? This is 16. Current top of the stack is 0000, 0001. 6 is 0110. E is 1110. If I'm not wrong, is equivalent. Binary is 1110. This is base 2. Okay. Now, so far we segregated the things very well. Now we need to identify the answer. Okay. The question is, the call instruction is of two codes. The first word is the opcode and second word is the starting address of the subroutine. One word is of 2 bytes. When the call instruction happens, the stack pointer, the stack will be updated with two things. Current PC will be pushed into the stack. Current PSW will be pushed into the stack. That is, during the execution course of the instruction, a program, when a subroutine is called, we know that the program counter value must be saved somewhere. Of course, that provision is a stack. When a routine calls a subroutine, generally, before we branch to the subroutine, we should be able to save the program counter. The program counter storage provision is a stack. So here is a somewhat customized. In addition to saving the program counter, he is also saving PSW. What is PSW? PSW is nothing but our flag register. Okay, generally we don't save the flag register during a subroutine call. Only during a service routine call, that is during the interrupt only, we will save this flag. But according to the question, when a call instruction is executed, two things will be saved into the stack. One is program counter, one more is PSW. Let us go to our stack. Okay, here on 016, on the top of that, first program counter will be pushed, after which PSW will be pushed, right? Got me? Initially, once again, just recall, stack is implemented from 0100 and current top of the stack is 0160. That means that at 0160 there is an element, final element, before the stack is being pushed with two more elements during the call instruction. So right after which a call instruction is executed. As a result of the call instruction, two elements are pushed into the stack. One is program counter, one is PSW. So stack pointer will be stack pointer plus 2, right? This is the general thing. But because we added two elements to the stack, so stack pointer should be updated as stack pointer plus 2. But here we also provided with some important detail that it is byte addressable memory. What is byte addressable memory? Every byte will be given an address, and one word as given in the question is equal to 16 bits. So every time in the memory, the displacement will be equal to 2. If you want to move from one location to another location, there will be displacement of 2. That is, initially, when you push one element into the stack, it will be stack pointer plus 2. It is just for only one element, because one location in the main memory is equal to 16 bits and 2 bytes. As each and every byte given an address, stack pointer will be equal to stack pointer plus 2 in case of just one element. But we added two more elements to the stack. So SP is equal to SP plus 2 for once. This is for program counter. SP plus 2 for one more time. This is for PSW. Now the stack pointer is equal to stack pointer plus 4, right? So now what is the question asked? What is the value of the stack pointer right after we execute this instruction, call instruction? So what we need to do is we need to add 0100 for this. So what would be the answer if we add 4? I'm just not adding, not to save the time. I'm just directly giving you that. Simply you just need to add. Will be the correct answer. So only the thing is we should be able to add 4 to the stack pointer. If you add 4, you will get exact answer, that is 017216. You just do it. Can I move to the next question? Did you understand? Did you understand this? Can I go to the next question? Shall we go to the next question? Bhumi, Anu, just participate. I just want you people to say yes or no. You want me to explain for one more time? I will explain as many times as possible. Anu, you there? Arnab, Anjali. Okay then, fine. I am going to the next question. Yeah. The most suitable addressing mode among the following to write the position independent code. And okay, fine. Stay focused. I think you might have gone through many of the addressing modes, right? Because addressing modes, why we do require addressing modes? This is one fundamental question which irritates you when we go through all these addressing modes. Being a programmer, we are very happy with the direct addressing mode. If it is immediate addressing mode, we'll be more happy. But why all these addressing modes irritates us? Let me tell you. If there are no addressing modes, there are no features of a program. You can't even declare a pointer. There is no pointer if there is no indirect addressing mode. That is the origin. Let me tell you, if there is no indirect addressing mode, no memory. You understand this? Every of the location in the main memory will be accessed somehow or the other by a pointer only. Right from the indirect addressing mode onwards, every other addressing mode more or less use pointers. That is indirect addressing mode. Making sense or not? Okay. So here position independent code he is talking about. Sir, what is position independent code? I will ask you something. That is, let us say you just, yeah, I know that your relative is correct. No, relative? Relative addressing mode. Yeah, I'm with you. Okay. But let me explain something here. Anu, you have written a program. Anjali, you have written a program. Satyam, you have written a program. In your C, let us say C program. Okay. Mr. Satyam has written a program here. Stay focused and listen. Now, this is Satyam's program. He did not store into the main memory. Satyam's program has 100 instructions. That is from 1 to 100. Okay. Now Satyam wants to make a call from the 4th instruction. From the 4th instruction, he just want to jump to the 10th instruction. Okay. He can directly write call here. Call 10th instruction. But when he performs call 10, what happens? Within his program, it will be 10th instruction. But when it is loaded into the main memory, if we write the same call 10, that call to the 10 will be leading to some other instruction, because this 10th instruction, that is the 10th location of the main memory, definitely not belongs to this program, right? Did I make it myself clear or not? Am I clear? That is the very reason why, in order to, branch appropriately, we either can take relative addressing mode or base register addressing mode. These are the two addressing modes are programmer friendly. These are the two addressing modes will give a confidence to the programmer that no matter wherever the program gets loaded, the branches will be taken appropriately. In the relative addressing mode, we will use the program counter, right? Program counter, this relative addressing mode can also be called as a PC relative addressing mode. That is, displacement which is given in the instruction plus program counter will take you to the appropriate location. Base register addressing mode is very simple. That is, either you can use relative addressing mode or base register addressing mode. In case of base register addressing mode, the moment when a program is being loaded into the main memory, the offset of the program will be loaded into the base register. Let us say your program is getting loaded from 450. Okay, this 450 will be loaded into the base register within the CPU. Okay, base register is 450, meaning what? The program is starting from 450th location. After which, every time when a branch has been, instruction is being executed, the offset which is given in that instruction will be added to the base register's content. So 450 plus 10, which is equal to 460, is the exact 10th location where he wants to branch for. So there are two addressing modes, which are programmer friendly addressing modes to write the position independent code. He don't need to be worried about where his program is being loaded into the main memory. So he can use either program counter. So at that time, when he uses the program counter addressing mode, this offset must be appropriately written. Okay, as offset plus, rather, the displacement plus program counter will give you the target address. This, displacement must be written as target address minus program counter, so that when you add this both, you will get a target address. I hope you got my point very clear. Yes or no? Bhumi, I didn't understand your question. Can you get it more enhance this? Then, okay, forget about everything. There are two addressing modes. One is relative addressing mode. One more is base register addressing mode, which makes a programmer can write position independent code. Okay. Next, can I go to the next question? Bhumi, Satyam, Arnab. Yeah. Let a register A contains the value 0101 1010 and the register B contains the value 0011 1100. An arithmetic addition is performed in ALU, that is A plus B. What are the values of the flags Z as CV after it gets updated as the operation gets finished in the ALU? I'll give you 2 minutes. Can you solve it for me? Can you solve it for me? Register A is something and register B is something. When you add it, what will be the flag values of Z as CV? Z stands for 0 flag. S stands for sign flag. Okay, Z is not given, right? Only just sign carry overflow. You just forget about the 0 flag. 0 is not given because in the options we got only 3. What is the sign flag? What is the carry flag? What is the overflow flag? I just want the answer for this. Let us straight away, without wasting any time, let me solve this. 0011 1100. This is register A. What is register B? Register B is, okay, this is register B, whatever. Register A is 0101 1010. Okay. Now let's add this. 000, 011, 100, 11, 01, 111, 11, 11, 10, 11, 10. Okay, this is 1. Here, you might have heard about overflow, right? What is overflow? What is overflow? You might have been talking about XR gate or doing carry in and carry out XRing. No, you don't need to do anything. Let me tell you one simple logic in order to understand what is the overflow. If the sign bit is reversed, that is the overflow. Got my point? You don't need to go for any XR or XNOR or anything. You just forget about everything. If the sign digit is reversed, sign digit should not be reversed. During and after the operation, sign digit should be the same. Two positive values are being added. Result should also be a positive value. There is no negative, but we got a negative value here. So that means that there is an overflow. I hope I made it myself clear. You talk about XR gate or XNOR gate doing, carry in, carry out XR. Talk about anything. It's just simply talking. That it will simply say you that if there is an abnormal sign reversal, accidental sign reversal during any operation which actually contradicts the actual sign, there will be a situation called overflow. We are in a situation called overflow. So here there will be overflow. Overflow bit must be equal to 1. There is no carry. Carry meaning we need to have an additional digit. So this must be 0. And a sign, of course, the most significant digit is equal to 1. This is equal to 1. 101A is the correct option. Yes? Teja, may I know what is your question? The third bit addition, maybe 1. What is third bit addition? Did I make 0, 0, 0, 0, 1, 1, 1, 0? Okay, yes. You are correct. 1, 0, 1, 1, 1, 0. Yes. Double 1, 0. So I missed it. Fine. Finally, this is important, but anyhow, 1, 0 must be equal to 1. So by the flow, I went by the flow. Some, it is a bigger pattern. I just corrected it. Is that the same thing you want to say? Of course, I guess so. Can you go to the next question? Can I go to the next question? Yeah. Consider new instruction name branch on bit set. The instruction BBS register POS label jumps to the label if the bit in position POS of the register operand in the register is equal to 1. A register is 32 bits wide and the bits are numbered 0 to 31. Bit in position 0 being the least significant. Consider the following emulation of this instruction on a process that does not have a BBS implemented. Very good question. Yeah. After a long time, I'm just looking at this question. Fine. Temp register mask branch to label if temp non-zero. The variable temp is a temporary register. For correct emulation, the variable mask must be generated by what? Okay. This is the question. So, what this question is talking about? Okay. Any answers? Any ideas? Any ideas? What is the option for this? What is the answer for this? First of all, did you understand this question? Did you understand this question? Yeah. Let me tell you. I know that it just the sentence framing is a bit complicated to understand this question, but it is also a simple question. Only the thing is we need to get into the right logic. Okay. There is a new instruction called BBS. Let us say somebody designed a new processor. Let us say myself, Anil Prasad, has designed a new processor. I named the processor as AP processor. When I design this processor, I will have my own set of machine language instructions, right? So I will design some customized instructions in which BBS is one of those instructions. How this BBS works? Let us have a look at this question. BBS REG POS label. It's a branch instruction, he's saying. Branch instruction, he's saying. So how it works exactly? Let us have a look at BBS register R2, some register of the processor will be specified here, and POS, the position number will be specified here, and a label. some branch address will be, subroutine address will be specified here. Okay. Now, if the current instruction is BBS R2 to 450, then this is the branch address, target address. We will be branching to 450th location of the main memory. If second position of R2 is 1, okay, branch on bit set in the register 2. If the second bit is equal to 1, then we need to branch to 450. Otherwise, we don't need to branch. This is the conditional branch instruction. So this is fine. Did you understand so far? Did you understand it so far? Did you understand? At least now. BBS as given, it's a conditional branch instruction. When BBS is given, there will be 3 parameters. There will be 3 operands. The first one is register. Some register will be specified, followed by the position, a bit position. A bit position will also be specified, right after which target address will be specified. If this bit position in the given register is 1, then we need to branch. Otherwise, we don't need to branch. Okay, so okay, fine. I will write the register. Okay, let us say register 2. It's a, let us say, 4-bit register. 1, 2, 3, 4. Let us say this is the first bit, this is the second bit, third bit, fourth bit. Okay, for that, this register 2 will be checked. In this 1, 0, 1, 0. This is the contents of the register. Immediately, the control of the computer system will come to this register. In this register, it will observe what is the position they are finding. They want to find it out. They want to check. They want to check second bit position. Okay, they will check the second bit position. If the second bit position is equal to 1, if the second bit value is equal to 1, then they will take this branch. Otherwise, they don't take the branch. Next instruction will be executed. Yes or no? Got my point? Okay, so this is how BBS works. Now understand carefully. Consider the following emulation with this instructional process that does not have a BBS implemented. Now he has come back to a normal processor which doesn't have BBS at all. When there is no BBS, how the same thing is going to be followed? How the same BBS is going to get executed? This is the question. Now let us forget about all these things. We will come back and understand this question. Okay. Now let me take you to illustrative slide and be sensible in understanding this. One fundamental question, one very basic simplest question I want to ask you guys. You don't have anything in your hand, but I ask you people, Bhumi, you go and find out what is the bit position of a register. Since you are not a human being, since you are a processor, you need to answer me immediately what is the bit position of that corresponding register. What I told. I asked, let us say, Anu or Satya or Shiva, that I just asked you, you people are CPUs, you are not human beings, okay? You can't look at it and tell me what is the second bit in R2. So being a CPU, you should follow some mechanisms to find out what is the bit position of R2. I'll tell you, I'll ask you what are the mechanisms that you follow. The simplest mechanism, if you're being sensible, is you will take one more register. Let us say this is R2. In R2, I have some, let us say it's a 4-bit register. I can't draw all 32 bits. My hand will go off. So let us say randomly I'm putting 0, 1, 0, 1. Okay. This is second bit position I want, let us say. In order to find out what is the second bit, what you will do, you will take one more register. Okay. Which has a 1 in the second bit position and all zeros in the remaining bits. Then when you perform AND operation in between these two registers, if the resultant register has a 1 inside, then that means that second bit position in the register what you want to check is equal to 1. If there is no 1 in the resultant register, if all are equal to zeros, that means that in the second bit position you have a 0. Did I make it myself clear, or you want me to repeat? Yes, absolutely. We will take mask register in which we will insert a 1 in the desired bit position. In the desired bit position, we will insert 1. Then we will perform AND operation in between the register in which what we want to check, in which we want to check this bit position value. Finally, the result we are going to obtain into the destination register. If the destination register has a 1 in that bit position, then we have the corresponding bit position where we want to check is 1. Otherwise, it will be 0. Clear? Anu? Clear, Bhumi? Clear, Arnab? Yes or no? You want me to repeat? I will repeat as many times as possible to make you people completely getting into this. Anu, did you get it? Get this? Arnab? Yep. Listen. Stay focused. Once again, let me give you the same example. There is some register, X register in the system. Okay. Mr. Arnab, you want to find out what is second bit position in the X. Okay. If you actually think sensible, it will be very easy. Second bit position, let us say now I am changing my bit position where I want to check what is the value. This is the third bit. Okay. This is the second bit. This is the first bit. This is the fourth bit. In the third bit, you need to find out what is the value. For that, what you will do is, you will take a mask register. What is a mask register? In the mask register, all will be 0. Okay. And you will insert 1 exactly at the position where you want to check. Okay. In the X register, you are going to insert 1. In the third bit position, you already inserted 1. Now you are going to perform an AND operation in between. Did you get it? Now, result you check. Let us say, in the third bit position, if it is equal to 1, rest of all the values in the resultant register will be equal to 0 except the third bit. If the third bit has a 0 in the X register, including all the bits, the third bit will also be equal to 0. If the resultant register has a 1 in it, that means that in the X register, the corresponding bit position what you want to check has a 1. I hope I made it myself clear. Yes or no? Yeah. So, that is what? Simple. In the mask register, okay, we need to left shift 1 for position times. So, option A is correct. Initially, we are going to take a mask register. Mask register, has all zeros. Now, what we need to do in order to insert 1 at the corresponding bit, let us say I'm just taking only 4-bit register, 1, 2, 3, 4. To the second bit position, I need to shift 1. Initially, I will perform left shift with 1. So, if I perform left shift with 1, the first bit position will be equal to 0, rest of will be equal to, the first bit position will be equal to 1, first bit value will be equal to 1, rest of the bits will be equal to 0. Then you perform one more shift. So, this 1 will go here, here a 0 will be inserted, this is 0 and this is 0. So, we will take mask and we need to left shift 1 to position times. So, second bit, for the second bit you need to insert 1. So, 2 times you need to perform left shift. So, mask register will exactly have 1 in the desired bit position, after which this register and mask, this temporary register and your mask will give you the desired result. I hope. R with 0, you can't perform R with 0. Why R cannot be performed? AND will only give you the bit position if it is getting ended with 1. R will, let us say I am performing R. Okay, R will give you all the bit positions as 1, right? R is not possible, Satyam. Only we need to perform ending. Got me? R is not at all possible. How R is possible? Let us say, as I am just going with Satyam, I want to replace this end with R. In every, let us say, if R is what? 0 plus 1 is equal to 1. Resultant will be equal to 1 in every place where we do have a 1 in X register. Okay. Desired bit, no. Understand, here POS is mentioned. What is POS? POS is 2. Let us say in our case, position, for position number of times, 1 must be left shifted. That is what I told you, missed the point. How many times 1 should be left shifted? See, this 1 must be inserted in the second bit position, right? I can't have this 1 in any bit position. I just need to have this 1 at the second bit position. So 2 times I need to left shift. For position times, what is position? Position is 2. Got me? Did you understand? Yeah. Can I go to the next question? Yeah. A certain process supports only immediate and direct addressing mode. Which of the following programming language features cannot be implemented on this processor? Yeah. The first one is pointer, arrays, records, recursive procedures with local variables. Which is not possible, tell me. This question is for you. I don't want to explain. Anu, answer me. Arnab, answer me. Satyam and Anjali, Bhumi. I want you people to answer me correctly. A, B, C, D. Can you convince me? After one there is O. Where is the previous question? This is 0. Mask is 0, right? How you represent mask register? Without MASK? Bhumi? Without MASK, how you represent a mask register? If you want to represent with zeros and ones? Mask is 0, right? To 0th register, for position times you are inserting. Register transfer language. Ma'am, Bhumi? Getting? Did you understand, Bhumi? I just need to go to the next question quickly because we are running out of the time. Yeah. After D, see, listen. Supports immediate and direct addressing. Immediate is this. Let us say this processor can support only two features of the program. That is immediate, meaning constants. Programming language can implement constants. The programming language can implement variables. Other than this, nothing is possible. Nothing is possible at all. Pointers are not possible, arrays are not possible, records are not possible, recursive procedures with the local variables, it is not possible. For pointers, I require indirect. What is happening? Yeah. For the pointers, I require indirect addressing mode. Without indirect addressing mode, there are no pointers. For arrays, I require indexed addressing mode. If there is no indexed addressing mode, there is no arrays at all. For records, still I do require pointers. How you get the elements of the records? The records, understand, the records will be available in the data part of the main memory. If it is available in the data part of the main memory, in order to retrieve an element, I do require a pointer, because the data part of the main memory, I told you in one of my previous sessions very clearly that data part of the main memory is non-contiguous. So the records are scattered across the main memory. Let us say there are 10 elements in a record. All these 10 elements cannot be available in the contiguous locations. One element may be available at the 450th location. One more element is available at 550. One more element is available at 475. So elements of the records can be poised across all the data memory. So in such case, we do require pointers. We do require linked list. These records will be implemented by using some of the data structure. If you want to use a data structure, pointer is a must, right? So even for the records, I do require a pointer. Recursive procedure with the local variables. What is the recursive procedure with the local variables? Understand carefully. I need to have a stack where when a program is calling a subroutine, a routine calling a subroutine, where the current program counter value is going to be saved. The current program counter value will be saved always in a stack. Okay, stack is going to have your program counter, and in addition to which, stack will also have the program's local variables. If you want to store the local variables and the program counter values when a program calls routine calls a subroutine, I do require a stack. Even without a stack, routine can call a subroutine, but recursive procedure can never happen without a stack. How? I'm going to explain in some other sessions, but if you want to implement recursive procedure with the local variables, I do require a stack. Okay. If you want to access a stack, I do require a stack pointer. Pointer can only be achieved by having only indirect addressing mode. There is no indirect addressing mode at all. So none of the pointers, nor arrays, nor records, nor recursive procedures with local variables, nothing is possible. Got my point? So D is the correct option. Can I go to the next question? Simple. Without pointers, you can't execute a program. Simple. You can't use the computer system at all. Even if you want to load, let us say, forget about accessing the computer system, forget about accessing your program, forget about accessing a pointer. First of all, if you want to load your program from secondary memory to the main memory, I do require a pointer. If my processor doesn't support pointer, forget about loading the program even into the main memory. None of the above are possible. Okay. Good evening, Nisha. Yeah. Next thing. Consider the following data path of a simple non-pipeline CPU. The registers A, B, A1, A2, MDR, the bus and the ALU are 8-bit wide. The mux is of 8:2:1 and a demux of size 8:1:2. Each memory operation takes two CPU clock cycles and uses MAR and MDR. Stack pointer can be decremented locally. Fine. Here he is showing one ALU. Okay. Is ALU visible completely? I hope it is so. The CPU instruction push R, where R is equal to A or B, has a specification. Memory of SP, sorry, R value will get transferred to memory of SP, and SP will be updated with SP minus 1. How many CPU cycles? What actually is that? How many CPU clock cycles are needed to execute the push R instruction? 1, 3, 4, 5. What is the option? What is the option? How many CPU clock cycles are needed to execute push R instruction? Can I explain? Shall we start? Or do you have any idea what is the answer for this? This is also the simplest question if you actually have at least a minimal idea about a CPU design. But nevertheless, I'm going to give you, the entire detail within a no time. Stay focused and understand. Can I? Yeah. So understand this thing. Simply. Just a minute. Just a minute. Yeah. Understand this carefully. Yeah, no doubts. Stay focused here. See here. Consider the following data path of a simple non-pipeline CPU. Registers A, B, A1 are A2, memory data register, and the bus of the ALU are 8-bit wide. All are 8 bits. A, B, A1, A2, memory data register, and the bus system and the ALU are 8-bit wide. ALU is also of 8 bits. Understand? Consider this. I will write it here. All are 8-bit. Simply, I can write that all are 8 bits except stack pointer and MAR, right? MAR are 16-bit registers. 16-bit registers. Okay. Each memory operation takes 2 clock cycles. In order to communicate with the main memory, just a minute. What is technical glitch? Yeah. Once again, spare me some technical glitch is there. So without my knowledge, this is moving. So you need to spare me. For tomorrow's session, I will make sure that this doesn't happen. DR is equal to 8 bits. Okay. And what are this? What are this? MAR. I do have MAR and SP, stack pointer, are 16 bits. Alright? Now stay focused here. Stay focused here. Yeah. Now the question is push R where R is equal to ARB has a specification. R will be transferred to memory of SP, okay, and SP will get decremented. R is a register A will have to be pushed into memory of SP. Okay, stack pointer is the register. Stack pointer is going to specify a memory address on which the top of the memory stack is mentioned. Let us say stack SP is 450. Okay, to the 450, the contents of A must be pushed. For this, actually, how many clock cycles are actually required? How many clock cycles are actually required? This is the question. So in order to perform this, let me tell you straight away, D is the correct option. I do require 5 clock cycles. First of all, any CPU, understand, any CPU nowadays is using 2 registers. Look at this CPU, look at this ALU and the CPU, the registers. Any CPU nowadays is using 2 registers. One is memory address register, MAR. One more is memory data register, MDR. Okay, to communicate with the main memory. Let us say from CPU to the main memory, if you want to send one data, first of all, memory address register should be loaded with an address. After which memory data register should be loaded with the data. After which memory address register will locate the main memory with a specific address. After which the memory data register, the data will get transferred to that specific address register which is specified by the memory address register. This is the fundamental thing that you need to understand in order to understand the logic of CPU to memory transfer. Not only in this question, in any question in any CPU. So in order to communicate with the main memory, I do require a MAR and I do require an MDR. Did you understand this? Option D, 5 clock cycles. That it is 8 bits. Look at this question, 8-bit wide. Arnab, I did not pretend, I did not assume. This is 8-bit as given in the question. Yes, 5 clock cycles is correct. Okay. Now initially what will happen? I need to transfer address to memory address register. So from stack pointer to memory address register, I need to transfer the address. What is the size of the stack pointer? Size of the stack pointer is equal to 16 bits. But the bus system is of just 8 bits. So in order to transfer the stack pointer value to the memory address register, I require 2 clock cycles. Right? Did I make it myself clear? Next thing is, I need to load memory data register with A. And I do require only 1 clock cycle for this because A and the memory data register are of just 8 bits. So I don't need to have any worry at all. So the first one is memory address register need to get the value from stack pointer and register A should be transferred to MDR. For this, I just need only 1 clock cycle because within 1 clock cycle, as the data bus is equal to 8 bits, I'll be able to completely send A to MDR. But for transferring SP to MAR, I require 2 clock cycle because 16 bits must be transferred. In the bus system, it supports only 8 bits at a time. In 1 clock cycle, 8 bits will get transferred. In the other clock cycle, 8 more bits will get transferred. So transferring SP to MAR, I do require 2 clock cycles. Transferring A to MDR, I do require 1 clock cycle. 3 clock cycle in order to load MAR and MDR. After that, it is clearly specified that it requires 2 CPU clock cycles in order to communicate with the main memory. So total 3 plus 2, 5. Got my point or not? Got my point or not? Yes or no? Can we go to the next question? Arnab, what hum? I just want you to be, completely okay with this. Yes. Bhumi, did you understand? Anu? Bhumi? Bhumi, you there or not? Fine. Can we go to the next question? I don't need to illustrate this slide. Consider a RISC machine where each instruction is exactly 4 bytes long. Conditional and unconditional branch instruction use PC relative addressing mode with offset specified in the byte to the target location of the branch instruction. Further, the offset is always with respect to the address of the next instruction of the program sequence. Consider the following instruction sequence. This is the first instruction, second instruction, third instruction, fourth instruction. This is the RISC machine. Okay. Now, in the RISC machine, what is given? There are 4 instructions. Exactly 4 bytes long. Each instruction is of 4 bytes. He don't need to tell us. RISC machine meaning one instruction size is equal to 32 bits. Conditional, unconditional branch instruction use relative addressing mode. What is relative addressing mode? Program counter value will be added to the offset of the offset that is specified in the branch instruction in order to calculate the effective address. That is how relative addressing mode will be calculated. Next thing is, further the offset is always with respect to the address of the next instruction. We know how relative addressing mode works. In the relative addressing mode, effective address is equal to program counter plus offset that is specified in the instruction. This is how effective address will be calculated, right? Now come to the question. If the target of the branch instruction is I, okay, then the decimal value of the offset is what? This is the question. Okay. Now the branch instruction is I plus 3. The fourth instruction is the branch instruction. And if it is a taken branch, the branch instruction will be the first instruction, that is I. If the I instruction is the target instruction, what is the offset he is asking for? Okay. Now it is very simple. You can clearly understand when we start, when we start writing this program. When we start writing this program, we will consider that the first instruction is available at the 0th location. Second instruction is available at the 4th location because one instruction is equal to 4 bytes, 32 bits, and each instruction will take 4 addresses in the byte addressing mode, right? RISC always follows byte addressing. Okay, second instruction is at the 4th address, third instruction is at the 8th address, fourth instruction is at the 12th address. Oh, where is this? Just a minute. Yeah. So now this is now program counter must be added to the offset in order to get the target address. So it will be very simple. Effective address is 0 plus program counter value. What is the program counter value? Program counter value is equal to 16. 16 plus some x. Now what is the effective address right now? Effective address is equal to 0. We are asked for the offset that is mentioned. X is equal to 0 minus 16, which is equal to minus 16. So option will be equal to minus 16. Did you understand this or not? Yes, minus 16 is correct. Minus 16 is correct. Here simple. Offset must be minus 16. Minus 16 plus 16 must be branching you to 0, right? Yes or no? Yeah, good, very good, very good. So can I go to the next question? Yeah. Consider the following sequence of micro operations: MBR PC to MBR, X is equal to MAR, Y is equal to PC, MBR to memory. Okay, these are the micro operations that are being happened now. Which one of the following is possible operation performed by the sequence? Instruction fetch, operand fetch, conditional branch, initiate of the interrupt service. Understand carefully. Now, program counter value is being saved somewhere. Straight away, you can understand this. When program counter value is being saved, it can happen only in 2 cases. First case, during a branch instruction, the program counter value will be saved into the stack. Second case, during a subroutine call. Okay, sorry, branch itself is a subroutine call. During an interrupt, service routine call. So program counter value will be saved in two cases. During the branch instruction, that is when a subroutine has been called by some other routine. One more is during an interrupt request. So what is this? Is it a branch instruction or an interrupt? We will see. Now program counter is transferred to MBR. Some X value will be stored into MAR. Program counter is completely being updated. Now MBR is getting transferred to memory. In the branch instructions, write it down. During the branches, program counter will be saved in register stack. Register stack in the CPU itself. Program counter cannot be stored into the main memory during the subroutine call. But during the interrupt, program counter will be sent to memory stack. Okay, so here the program counter is being transferred to the memory. That means that it's just nothing but an initiation of the interrupt service. Understand, there are only two cases where the program counter value will be saved. First case is branch instruction. Second case is interrupt during the call of the interrupt service routine. During the interrupts. For the branching, we don't send the program counter to the main memory. Within the CPU stack itself, we will save the program counter value. But during the interrupts, we will send this program counter value to the main memory. I hope you got my point. Okay. Dumi, do you understand this? So option D is correct. Write it down somewhere. This is a thumb rule. Being a CPU designer, you must always have been aware of this. Horizontal microprogramming does not require use of a signal decoders. Result in large sized micro instruction than vertical microprogramming. Uses 1 bit for each control signal. All of the above. What is this answer? What is the answer for this? What is the answer for this? Anu? Arnab? Krishna? Hey Krishna, tell me what is this answer? Any idea what is the horizontal microprogramming? D is correct. Hey, you people are spot on. Very great. Yeah. Two things. Vertical microprogramming, horizontal microprogramming. In the vertical microprogramming, n bits will give you 2 power n possible micro operations. Right? So vertical microprogramming is very simple and the control memory size is very less. But horizontal microprogramming, that's it. We need to turn the world upside down to design a micro operation. It is purely because every micro operation requires a separate bit. We need to collect more bits to design the control memory. So does not require use of signal decoder. Decoder will use only in the case if the signals are encoded. We don't use the encoders or decoders. Every bit represents a separate micro operation. Okay. Result in the larger size micro instruction. Biggest disadvantage. Uses 1 bit for each control signal. So A, B, C, all the above are the correct options. All the correct options. No, everything is correct. Does not require use the signal decoder. It doesn't. Signal decoders are not required because we don't encode. If n bits gives you 2 power n combination, then we do require encoders and decoders. When each digit requires to be stitched to one possible micro operation, we don't require either encoders or decoders. So results in, of course, the larger size micro instructions. Obviously, A, B are interrelated and these two will be related to the C. Use 1 bit for each control signal. Okay. Very simple. I don't need to enhance it much. Suppose a processor does not have any stack pointer register. Which one of the following statements is true? Tell me answer for this. Tell me the answer for this. that is always there. Good. Yeah. Suppose processor does not have any stack pointer register. Which one of the following statements is true? What is the answer for this? Come up quickly. Subroutine call, subroutine, but no nested subroutine calls are not possible, but interrupts are not. You there or not? Answering, going through the question or not? You people prepared for the gate for many days, taking much time. Fine. Let me tell you. See, let me tell you. If the programmer is provided with a stack, he will be very happy to use the stack, okay, to use it as a provision to store the program counter value during subroutine call or service routine call. Okay, subroutine meaning function calls another function. When a routine calls subroutine, program counter value will be saved. During the service routines also, during the interrupts also. When one program is going out, one more program is coming in, program's program counter must be saved. If the stack is provided, I will use. But if there is no stack, my life doesn't end. Even without stack, I can have several possibilities to store my program counter value. Stack makes my life easier, but doesn't end my life if I don't have one. Even without stack, I can have the storage provisions such as, I will write it here, write it down somewhere. In memory of 0, I can store program counter. Although I do have some shortcomings, program counter can be saved in memory of 0, but only one at a time. Routine A can call routine B. Routine B can call routine C with this convention. Only one routine strictly can call one more routine. That called routine should return back strictly back to the calling routine. This is M of 0. If this is not taken, I will use one more convention, that is offset of subroutine. I can use offset of subroutine to store my program counter value. At that time, the nested subroutine is also not possible, but not recursion. Stack, without stack, only recursion not possible. Without recursion, except recursion, every other thing, including subroutine call, service routine call, everything is possible. Only recursion is not possible. Okay. Stack, if you are provided with, being a programmer, you will be very happy because you don't need to go for any complexity. But stack doesn't provide you, meaning can't you execute a program? You will be able to, because we are provided with several other possibilities. So it's all the sequences of subroutine calls. Also interrupts are possible. D is the correct option. Okay. Next thing is, a CPU has two modes, privileged and non-privileged. In order to change the mode from privileged to non-privileged, understand carefully. This is kernel mode, user mode. Kernel and user. Understand, for changing the mode from user to kernel, I require a software interrupt. But from kernel to user, I don't require no interrupt. Okay, a non-privileged instruction is required. Don't fall under any trap. I don't require any software interrupt or hardware interrupt, some Cosmos interrupt or alien interrupt. I don't require interrupt at all, because here he asked that changing the mode from privileged to non-privileged, from the kernel to user mode, any normal instruction can take. Let us say add A. This is one instruction, after which printf. Printf is a privileged instruction, add A is a normal instruction. The control will switch the mode from user to kernel mode, from add A to printf. For that, software interrupt is needed. Right after printf, there is one more normal user instruction, that is add B. Okay, so only I do require software interrupt to change the mode from user to kernel, but not kernel to user. In order to change the mode from kernel to user, any non-privileged instruction would do, more than sufficient to me. So option D is the correct option. Okay, in the absolute addressing mode, this is the one of fundamental question. I don't need to answer this. At least for this question, I can save my tone, I can save my voice, I guess so. Sorry, answer this. What is the absolute addressing mode? Right? Or do you differ? Do you have any contradictions? Absolute addressing mode, direct addressing mode. We do have a memory address specified in the instruction, right? Option A is correct. Direct addressing mode will have operand's address. Hey, this operand is not inside the instruction, excuse me. The address of the operand is inside the instruction. Oh, very, very sorry. Absolute addressing mode is a synonym for direct addressing. Okay, direct addressing mode or absolute addressing mode are one and the same, because the address of the operand is specified within the instruction. Beg your pardon, A is not correct, B is correct. Okay, I hope I made myself clear. Next one is, on receiving an interrupt from an IO device, what is the job of the CPU? Will the CPU be halted for a predetermined time? will the CPU hands over the control of the address bus and data bus to the interrupting device? Will it branches off to the interrupt service routine immediately, or will it branch off to the interrupt service routine after completion of the instruction? Answer this so that we will finish it up. Option D is correct because it doesn't halt. Computer system doesn't get halted for no matter what unless there is a halt instruction. Unless there is a halt instruction, the computer system doesn't halt. Hands over the control of address bus and data bus to the interrupting device. It doesn't hand over address bus and data bus to nobody except during a DMA request. Only during a DMA request, CPU will hand over the address bus and data bus. Here there is no specification of the, no, he did not specify DMA, so it is not correct. Branch off to the interrupt service routine immediately. Is it possible? If I am a CPU, if I am interrupted, will I go to the interrupt service routine immediately? No. The moment I get interrupted, I say, please hold on. I am doing some important thing here. Right after I finish, I will come to you. What is the important thing that I am doing? The important thing for the CPU concurrently is to finish off the current instruction. Unless the current instruction gets finished, no CPU in the world will branch off to the interrupt service routine. Interrupt will only be serviced right after finishing the current instruction. So option D is correct. I'll tell you why also. We know every CPU knows only the address of the next instruction. Okay. No CPU knows the address of the current instruction. That is the reason why the moment we receive the instruction, the address of the instruction will be erased. So there is no ever way for any CPU to fetch the current instruction again. So in order to service the interrupt, first of all, every CPU must be able to finish the current instruction, because the only provision associated with the current program is program counter. The only knowledge that we do have is the program counter, which is the address of the next instruction. So next instruction can be fetched when I come back to execute this program, but not the current instruction. Current instruction should always be executed. I hope I made it myself clear. With this, we have come to an end of this current session. I think that it is productive and potential. I covered almost every aspect of the CPU design. Just go through any of the question, any of the doubts. You can just you can message me at any point of period. And yeah, that's it from my side. Any doubts? If there are no doubts, yeah, tomorrow we are going to completely get into the details of the memory. Okay, tomorrow is an important session because memory has a lot of aspects to be covered. So stay focused and come back exactly at the time. So we will cover as many questions as possible in memory. Thank you, and that's it for the day.